Hi everyone. In this video we will continue to discuss about the ARM processor for the part 2, firstly, about flip-flop. A flip-flop is a bistable electronic circuit capable of storing one of two logical states, typically represented as 1 or 0, true or false, high or low, etc. Once set to a particular state by an input signal, often a voltage change, the flip-flop will maintain that state until another input signal changes it. The D-type flip-flop, as you highlighted, is one of the most widely used types in computer logic. The D stands for data, emphasizing its role in storing and manipulating binary data within digital systems. In a D-type flip-flop, the data input, D, determines the state the flip-flop will store when triggered by a clock signal. This makes it versatile for various applications in digital circuits, including data storage, synchronization, and state machine implementations. The bistable nature of flip-flops is what makes them particularly valuable in digital electronics. Their ability to maintain a stable state until instructed to change allows for precise timing and sequencing of operations within digital systems, essential for tasks such as data processing, control, and communication. Overall, flip-flops serve as the backbone of sequential logic circuits, enabling the storage and manipulation of binary data in modern computer systems. Their reliability, versatility, and efficiency make them indispensable components in the field of digital electronics. By using this figure, we will discuss about the D-type flip-flop. In the diagram, D, data, input, this is the input line where the data to be stored in the flip-flop is provided. CLK, clock, input, this input signal controls when the data at the D input is captured or latched by the flip-flop. Q output, this is the output line that represents the stored data bit. Q bar output, this is the complement of the Q output. Here's how a D flip-flop operates. 1. Initially, both the D input and the CLK input are at stable logic levels, either 0 or 1. 2. When the CLK input transitions from one logic level to another, e.g., rising edge or falling edge, it triggers the flip-flop to capture the data present at the D input. 3. If the D input is at logic 1 when the clock signal transitions occur, the flip-flop stores a logic 1 at its output, Q, and a logic 0 at its complemented output, Q bar. For conversely, if the D input is at logic 0 when the clock signal transitions occur, the flip-flop stores a logic 0 at its output, Q, and a logic 1 at its complemented output, Q bar. 5. Once the data is captured, it remains stored in the flip-flop until the next clock transition occurs, updating the output based on the new input data. This behavior allows the D flip-flop to store a single bit of data and retain it until instructed to update based on the clock signal. It's a fundamental building block in digital circuits. Used for various purposes such as data storage, synchronization, and state machine implementations, this is a basic overview of how a D flip-flop works. In practice, flip-flops may have additional features such as asynchronous clear and preset inputs for more complex functionality. A shift register is a sequential logic circuit that stores and shifts binary data bits along a chain of flip-flops. It's a fundamental building block in digital electronics, commonly used for tasks such as serial to parallel conversion, data storage, and data manipulation. Let's explore how a basic shift register operates. Flip-flops. A shift register typically consists of a series of D flip-flops connected in cascade, forming a chain. Each flip-flop in the chain stores one bit of data, serial input, SI. This is the input line where new data bits are serially inputted into the shift register. The data is usually synchronized with a clock signal, parallel output, PO. This is the output line where the stored data bits are read out in parallel form. Each flip-flop's output contributes one bit to the parallel output, clock input, CLK. The clock signal controls the shifting operation of the shift register. It triggers the transfer of data from one flip-flop to the next. Here's how the shifting operation works. 1. Initially, all flip-flops in the shift register are reset to an initial state, typically all zeros. 2. When a new data bit is inputted at the serial input, SI, it enters the first flip-flop in the chain. 3. On each clock edge, The data stored in each flip-flop is transferred to the next flip-flop in the chain. This shifting operation propagates the data bits through the shift register, for as a result, the data bit that was initially inputted into the first flip-flop progresses through the chain. Advancing by one position with each clock edge, 5 the shifted out data bits can be read out in parallel form from the parallel output, PO, at any point in time. The number of flip-flops in the shift register determines the size of the shift register and the maximum number of bits it can store. Additionally, the direction of shifting, left or right, and other features such as parallel load, serial output, and feedback can be incorporated to enhance it. These are the basic steps involved in the execution of a program by the CPU. Let's delve into each step. 1. Fetch the first instruction. The CPU fetches the first instruction from the memory location specified by the program counter, PC, which points to the address of the next instruction to be executed. 2. Decode the instruction. Once the instruction is fetched, the CPU decodes it to determine the operation it specifies and the operands involved. This step involves interpreting the opcode, operation code, and any associated addressing modes or additional information. 3. Execute the instruction. After decoding, the CPU executes the instruction by performing the specified operation on the operands. This may involve arithmetic or logical operations, data transfers between registers or memory, control flow changes, or other tasks depending on the instruction's purpose. For fetch the next instruction. After executing the current instruction, the CPU increments the program counter, PC, to point to the address of the next instruction to be executed. It then fetches this next instruction from memory. 5. Decode the instruction. Similar to step 2, the CPU decodes the fetched instruction to determine its operation and operands. 6. Execute the instruction. The CPU proceeds to execute the decoded instruction, as in step 3. These steps form a loop that continues until the program reaches its end or encounters a branch or jump instruction that alters the normal sequential flow of execution. At each iteration of the loop, the CPU fetches, decodes, and executes instructions, advancing the program's execution one instruction at a time. This process is known as the instruction cycle or fetch-decode-execute cycle and is fundamental to the operation of modern CPUs. It enables the CPU to execute programs stored in memory by sequentially processing instructions, performing the specified operations, and advancing the program's execution in a controlled manner. Machine instructions are the fundamental building blocks of computer programs, each specifying a particular operation or action to be performed by the CPU. Here's a breakdown of some common types of machine instructions and their purposes. 1. Arithmetic instructions. These instructions perform basic arithmetic operations on data, such as addition, subtraction, multiplication, and division. They operate on binary values stored in registers or memory locations and update the result accordingly. 2. Logical instructions. Logical instructions perform bitwise logical operations on binary values. This includes operations like AND, OR, XOR, and NOT, which manipulate individual bits in binary data to perform tasks like data masking. Bitwise comparison, and logical operations. 3. Shift instructions. Shift instructions shift the bits of a binary value to the left or right by a specified number of positions. This can be used for tasks like multiplying or dividing by powers of 2, extracting or inserting specific bit fields, and manipulating binary representations of numbers. For data transfer instructions, these instructions move data between registers, memory locations, and input/output devices. They include instructions for loading data from memory into registers, storing data from registers into memory, moving data between different registers, and transferring data to and from input/output devices. 5. Comparison instructions. Comparison instructions compare values against constants or other values and set flags or condition codes based on the result. This allows for conditional branching and decision-making based on the outcome of comparisons. 6. Control instructions. Control instructions are used to control the flow of program execution. They include instructions for branching to different parts of the program based on conditions, conditional branching, jumping to specific locations, unconditional branching, and performing subroutine calls and returns. Modern CPUs are equipped with specialized subsystems, each optimized for handling specific types of machine instructions efficiently. These subsystems include 1. Arithmetic Logic Unit (ALU). The ALU is responsible for performing basic arithmetic operations, such as addition, subtraction, multiplication, and division, and logical operations, such as AND, OR, XOR, and NOT, on integer data. It operates on binary values stored in registers and performs calculations based on the instructions provided by the CPU. 2. Floating Point Unit (FPU). The FPU is dedicated to performing floating-point arithmetic operations, which involve numbers with fractional parts or numbers expressed in scientific notation, e.g., 1.23 times 10 to the power of 5. Floating-point operations include addition, subtraction, multiplication, division, and various mathematical functions like square roots, logarithms, and trigonometric functions. 3. Single Instruction, Multiple Data (SIMD) Unit. The SIMD unit is designed to execute SIMD instructions, which perform parallel operations on multiple data values simultaneously. These operations are typically performed on vectors or arrays of data, allowing for efficient processing of large datasets in parallel. SIMD instructions are essential in multimedia applications, such as audio and video processing, where large amounts of data need to be processed quickly, by offloading specific types of computations to dedicated subsystems like the ALU. FPU, and SIMD unit. Modern CPUs can achieve higher performance and efficiency in executing different types of instructions. This specialization allows CPUs to handle a wide range of computational tasks effectively, from basic arithmetic and logical operations to complex floating-point calculations and parallel processing tasks. Branch instructions are a crucial aspect of program control flow, enabling the program to change its execution path based on conditions or results of previous computations. These instructions allow the program to skip forward or backward in the sequence of machine instructions, thereby altering the program's flow of execution. Here's how branch instructions work. 1. Conditional branching. Conditional branch instructions enable the program to make decisions based on the result of a comparison or a condition. If a specific condition is met, e.g., a comparison yields true, the CPU executes the branch instruction, causing the program to jump to a different instruction address in memory. If the condition is not met, the CPU continues executing the instruction sequentially. 2. Unconditional branching. Unconditional branch instructions, also known as jump instructions, cause the program to unconditionally jump to a specified instruction address in memory. Unlike conditional branches, unconditional branches do not depend on any conditions or results, they simply cause the program to jump to the specified address, regardless of the current state. 3. Forward and backward branching. Branch instructions can cause the program to jump forward, to a higher memory address, or backward, to a lower memory address, in the instruction sequence. Forward branches are typically used for conditional jumps that skip over sections of code, while backward branches are often used for looping constructs such as while loops, for loops, and do-while loops, for flags and condition codes. Conditional branch instructions rely on flags or condition codes set by previous instructions to determine whether to take the branch. These flags represent the results of arithmetic, logical, or comparison operations performed by the CPU. Common flags include zero flag, Z, carry flag, C, sign flag, S, overflow flag, V, and parity flag, P. The CPU evaluates these flags when executing a conditional branch instruction to determine whether the specified condition is met. By using branch instructions and condition codes, programs can implement decision-making logic, loops, and other control flow constructs, enabling them to perform complex tasks and respond dynamically to changing conditions during execution. Branching is essential for implementing control structures like if statements, while loops, for loops, switch statements, and function calls in high-level programming languages. A system stack is indeed a crucial component in the operation of modern CPUs, including those based on the ARM architecture like the ARM11 used in the Raspberry Pi. The stack operates on the principle of last in first out, LIFO, where data items are pushed onto and popped off the stack in a reverse order. Here's how a system stack typically operates. 1. Push operation. When data needs to be stored temporarily, it is pushed onto the stack. This involves placing the data item onto the top of the stack. As a result, the stack pointer, a special register that points to the top of the stack, is incremented to point to the new topmost location. 2. Pop operation. When data needs to be retrieved or removed from the stack, it is popped off the stack. This involves accessing the data item at the top of the stack and removing it. As a result, the stack pointer is decremented to point to the new topmost location. The stack is typically used for various purposes in computer systems, including function calls. When a function is called, its return address and local variables are often pushed onto the stack. When the function completes execution, the return address is popped from the stack, and control is transferred back to the calling function. Subroutine calls. Similarly, when a subroutine or interrupt handler is invoked, its context, including registers and status flags, may be pushed onto the stack. Upon completion, the context is restored by popping the values off the stack. Data storage. The stack can also be used for temporary storage of data, such as intermediate results of computations or parameters passed to functions. The use of a system stack provides several benefits, including efficient memory management, support for nested function calls and subroutine invocations, and simplified program structure. It allows programs to manage and manipulate data in a structured and organized manner, facilitating the execution of complex tasks and the maintenance of program state. Overall, the system stack is a critical component in the operation of modern CPUs, enabling efficient memory management and supporting various programming constructs and execution paradigms. Let's delve deeper into the structure and operation of a stack in computer memory. 1. Base pointer. BP. The base pointer is a special register or memory location that points to the base or starting address of the stack in memory. Once initialized with an address, typically during program setup or initialization, the value of the base pointer remains constant throughout the program's execution. It serves as a reference point for accessing stack-related data and is used to calculate the relative positions of other stack elements. 2. Stack pointer, SP. The stack pointer is another special register or memory location that points to the current top of the stack. It indicates the memory location where the next data item will be pushed onto or popped off the stack. As data items are pushed onto the stack pointer is incremented to point to the next available memory location. Conversely, as data items are popped off the stack pointer is decremented to reflect the new top of the stack. Together, the base pointer and the stack pointer provide a mechanism for managing the stack in memory. The base pointer establishes the starting point of the stack, while the stack pointer dynamically adjusts to reflect changes in the stack size and contents. Here's a simplified example of how the base pointer and stack pointer work together. 1. Initially, both the base pointer and the stack pointer point to the same memory location, typically the base of the stack. 2. As data items are pushed onto the stack pointer is incremented to point to the next available memory location. 3. When accessing or modifying stack data, the base pointer is used as a reference point, allowing for calculations of the relative positions of stack elements. 4. As data items are popped off the stack pointer is decremented to reflect the removal of data from the top of the stack. By maintaining the base pointer and stack pointer, the CPU can effectively manage the allocation and deallocation of stack space, ensuring efficient storage and retrieval of data within the stack. This mechanism is essential for supporting function calls, local variable storage, and other stack-based operations in computer programs. Stacks are indeed invaluable for managing nested subroutine calls, also known as function calls within other functions. Let's dive into how stacks facilitate this functionality. 1. Nested subroutine calls. When a subroutine function is called within another subroutine, the CPU needs a way to keep track of the execution context of each subroutine. This includes parameters passed to the subroutine, local variables, and the return address, the address to which execution should return after the subroutine completes. 2. Stack usage. stacks provide a natural mechanism for managing this nested execution context. Each time a subroutine is called, its parameters, return address, and any local variables are typically pushed onto the stack. This creates a new stack frame or activation record for the subroutine on top of the existing stack. 3 stack frames. Each stack frame corresponds to a single invocation of a subroutine. As nested subroutine calls occur, additional stack frames are added on top of the existing ones, creating a nested structure resembling a stack of plates. For return addresses, when a subroutine completes its execution, the CPU pops the return address from the stack and jumps to that address to resume execution at the point immediately following the subroutine call. This allows the CPU to return control to the correct location in the calling subroutine. 5. Stack cleanup, after a subroutine returns. Its stack frame is typically removed from the stack by adjusting the stack pointer accordingly. This deallocates the memory used by the subroutine's parameters, local variables, and return address, effectively cleaning up the stack. Stacks play a crucial role in managing the temporary storage of data items and memory addresses during subroutine calls, also known as function calls or procedure calls. Here's how stacks are utilized during subroutine calls. 1. Temporary storage of data items. When a subroutine is called, the CPU typically needs to temporarily store certain data items, such as register values or parameters passed to the subroutine. These data items are often pushed onto the stack before the subroutine begins execution. This ensures that the data is preserved and can be accessed by the subroutine during its execution. 2. Temporary storage of memory addresses. Similarly, memory addresses or return addresses are also stored on the stack during subroutine calls. The return address is the address in memory where the CPU should resume execution after the subroutine completes its execution. By pushing the return address onto the stack before jumping to the subroutine, the CPU ensures that it can return to the correct location once the subroutine finishes executing. 3. Subroutine execution. Once the data items and return address are pushed onto the stack, the CPU jumps to the starting address of the subroutine and begins executing the sequence of actions defined by the subroutine. The subroutine performs its task, accesses the stored data items if necessary, and then prepares to return control to the calling code. 4. Stack cleanup. After the subroutine completes its execution, the CPU pops the return address and any other temporary data items from the stack. This process, often referred to as stack unwinding or stack cleanup, deallocates the memory used for storing subroutine-specific data and prepares the stack for subsequent subroutine calls or other operations. The system clock is indeed a vital component in the operation of a sequential circuit like a CPU. It provides the timing mechanism that synchronizes the various operations within the CPU, ensuring that different components work together harmoniously. Here's how the system clock and clock cycles facilitate the execution of operations within a CPU. 1. System clock. The system clock is a periodic signal generated by a clock oscillator circuit. It produces a series of pulses at regular intervals, typically measured in megahertz, megahertz, or gigahertz, gigahertz. The frequency of the clock signal determines the speed at which the CPU operates. 2. Clock cycle. Each pulse from the system clock represents a single clock cycle. The CPU's internal operations are synchronized to these clock cycles. During each clock cycle, the CPU performs specific tasks, such as fetching instructions, decoding instructions, executing instructions, and accessing memory or peripherals. 3. Instruction execution. The execution of instructions within the CPU is divided into discrete steps, each of which occurs during a clock cycle. For example, during the fetch phase, the CPU retrieves the next instruction from memory. During the decode phase, the CPU interprets the instruction and determines the operation to be performed. During the execute phase, the CPU performs the specified operation, such as arithmetic, logical, or data transfer operations. Additional phases may involve accessing memory or updating internal registers based on the instruction's requirements. For synchronization, the use of a system clock ensures that all operations within the CPU are synchronized and coordinated. This synchronization is essential for maintaining the integrity of data and ensure. 5. Clock speed. The speed of the system clock, measured in cycles per second, Hz, directly impacts the performance of the CPU. Higher clock speeds allow the CPU to execute instructions more quickly, leading to faster overall system performance. Overall, the system clock and clock cycles play a crucial role in the operation of a CPU, providing the timing framework that governs the execution of instructions and the coordination of internal operations. By synchronizing operations to the clock signal, the CPU can perform complex tasks efficiently and reliably, enabling the execution of programs and the operation of computer systems. Indeed, in the early days of computing, the execution of machine instructions often took a variable number of clock cycles, and some instructions required significantly more cycles to complete than others. This variability in execution time was primarily due to the architectural limitations and design choices of early CPUs. Here are some reasons why different instructions took different amounts of time to execute. 1. Instruction complexity. Instructions vary in complexity based on the operation they perform and the data they manipulate. Simple arithmetic or logical instructions, such as addition or bitwise AND, may require fewer clock cycles to execute compared to more complex instructions like multiplication or division. 2. Data dependencies. Some instructions depend on the results of previous instructions, leading to potential delays in their execution. For example, if a multiplication instruction follows an addition instruction, the CPU may need to wait for the addition to complete before it can begin the multiplication. 3. Resource contention. Early CPUs had limited resources, such as functional units and registers, which could become bottlenecks during instruction execution. Instructions that require access to these limited resources may experience longer execution times if they need to wait for them to become available. 4. Memory access. Accessing memory, especially external memory like RAM, is typically slower than accessing internal registers or cache memory. Instructions that involve memory access, such as load or store operations, may take longer to execute due to the additional latency associated with accessing memory. 5. Pipeline stalls. Early CPUs may experience pipeline stalls, where the pipeline is temporarily unable to progress due to various factors such as cache misses, branch mispredictions, or data hazards. These stalls can increase the overall latency of instruction execution. 6. Microarchitecture. The specific design and implementation of the CPU's microarchitecture can also impact instruction execution times. Different CPUs may employ different optimizations or trade-offs that affect the efficiency and speed of instruction execution. As CPU technology advanced, designers developed techniques to reduce instruction latency and improve overall performance. These advancements include techniques such as pipelining, superscalar execution, out-of-order execution, and faster memory access, which have helped reduce the variability in instruction execution times and improve the overall efficiency of modern CPUs. Why did different instructions take more time? Different instructions took more time to execute primarily due to variations in their complexity, resource requirements, and dependencies within the CPU architecture. Here are some reasons why different instructions might have taken more time. 1. Instruction complexity. Instructions vary in complexity based on the operation they perform. Simple arithmetic or logical instructions, such as addition or bitwise AND, typically require fewer clock cycles to execute compared to more complex instructions like multiplication, division, or floating point operations. Complex instructions involve more intricate algorithms and processing steps, which naturally take longer to complete. 2. Resource dependencies. Some instructions depend on the results of previous instructions or require access to specific CPU resources. For example, a multiplication instruction may require multiple clock cycles to perform its computation, as it involves more extensive operations and may require access to dedicated hardware units, such as the multiplier circuitry. Instructions that rely on the results of previous instructions may need to wait until those results are available before they can proceed, leading to increased execution time. 3. Memory access. Instructions that involve accessing memory, especially external memory like RAM, typically take longer to execute compared to operations performed solely within the CPU's registers or cache memory. Memory access involves additional latency due to the time required to access data from external storage devices, transfer it to the CPU, and perform the necessary read or write operations. Instructions that frequently access memory may experience longer execution times due to these memory access delays. 4. Resource contention. Early CPUs had limited resources, such as functional units, registers, and cache memory. Instructions that compete for access to these limited resources may experience delays if they need to wait for the resources to become available. For example, if multiple instructions require access to the same functional unit or register simultaneously, they may need to be scheduled sequentially, leading to increased execution times for some instructions. 5. Pipeline stalls. CPU pipelines can experience stalls or delays due to various factors such as cache misses, branch mispredictions, or data hazards. When a pipeline stall occurs, the CPU may be unable to progress until the issue causing the stall is resolved, resulting in increased latency for affected instructions. Instructions that encounter pipeline stalls may take longer to complete execution compared to instructions that execute smoothly through the pipeline. Overall, the time taken for an instruction to execute depends on a variety of factors, including its complexity, resource requirements, dependencies, and the specific characteristics of the CPU architecture. Designers strive to optimize instruction execution to minimize latency and improve overall CPU performance. The CPU does not operate as quickly as the clock speed demands. The clock speed can only be as fast as the CPU allows. The maximum clock speed of a CPU is determined by several factors related to its architecture, design, and manufacturing process. While the clock speed sets the pace at which the CPU processes instructions, the CPU's internal operations may not always keep up with the clock speed due to various limitations. Here are some reasons why the CPU may not operate as quickly as the clock speed demands. 1. Instruction latency. The execution of instructions within the CPU may take longer than a single clock cycle due to factors such as instruction complexity, resource dependencies, and memory access delays. Even though the clock speed defines the rate at which instructions are processed, some instructions may require multiple clock cycles to complete execution. 2. Pipeline stalls. CPU pipelines may experience stalls or delays due to various factors such as cache misses, branch mispredictions, or data hazards. When a pipeline stall occurs, the CPU may be unable to progress until the issue causing the stall is resolved, leading to inefficiencies and reduced throughput. Stalls can limit the effective utilization of the CPU's resources and prevent it from operating at its maximum clock speed. 3. Memory access delays. Accessing memory, especially external memory like RAM, typically involves additional latency due to the time required to fetch data from storage devices. Memory access delays can slow down the overall execution of instructions, especially if the CPU frequently accesses memory during program execution. The CPU may need to wait for memory access operations to complete before it can proceed with executing instructions, limiting its effective throughput. 4. Resource contention. Early CPUs had limited resources, such as functional units, registers, and cache memory. Instructions that compete for access to these limited resources may experience delays if they need to wait for the resources to become available. Resource contention can lead to inefficiencies and reduce the overall performance of the CPU, preventing it from operating at its maximum clock speed. 5. Microarchitecture limitations. The specific design and implementation of the CPU's microarchitecture can impact its ability to operate at high clock speeds. Some CPUs may be limited by architectural bottlenecks or design choices that prevent them from fully utilizing the available clock speed. Improvements in microarchitecture and manufacturing processes can help overcome these limitations and allow CPUs to operate at higher clock speeds. Overall, while the clock speed sets the theoretical maximum rate at which the CPU processes instructions, various factors can limit the CPU's ability to operate at its maximum clock speed in practice. Designers must carefully balance factors such as instruction latency, pipeline efficiency, memory access latency, and resource utilization to maximize the CPU's overall performance within the constraints imposed by its architecture and design.